Our discussion of adsorption or partitioning examined the absorption of neutral organic molecules from an aqueous solution into a solid phase. Such processes are governed primarily by the excess free energy of organic solutes in water, with the essential characteristic of the solid likely being its ease of access to solutes fleeing the aqueous solution. We next take up the topic of adsorption. For adsorption, a critical characteristic of the solid phase is its surface area. Because solutes are restricted to the surface or interface, solid phase concentrations are limited, producing competition between solutes and often solvent molecules for absorption sites. As a result, isotherms for such processes demonstrate decreasing slopes as solutes concentrate at solid surfaces. Here, the most common models for fitting adsorption isotherms, the Langmuir and Freundlich equations, will be reviewed. When adsorption is suspected, these really are the go-to models for fitting isotherm data. In a sense, they represent either end of the spectrum of adsorption behavior. The Langmuir model assumes homogeneous surfaces with constant heat adsorption values from the first sorbet to the last, while the Freundlich model assumes heterogeneity, for which the heat absorption changes as adsorption progresses. The successful fit of one versus the other provides important insights on the nature of the sorbent surface. The Langmuir equation is the most popular or commonly used model when fitting nonlinear isotherms for apparent adsorption processes. Shown here is the general shape of the isotherm curve. At low concentrations, the slope is positive and constant, but as solute concentration increases, the derivative of the isotherm begins a steady decline towards zero as it asymptotically moves towards a plateau. The Langmuir equation that fits the curve is shown here. Initially, we will treat it as an empirical function where A and B are defined as simply fitting parameters. It is instructive to examine the limiting cases for the equation, beginning with concentrations at or near infinite dilution for the solute. In this region, the equation reduces to a linear relationship where the solid phase solute concentration is directly proportional to that left behind in the aqueous phase. The proportionality constant is the fitting constant A, sometimes referred to as the intensity parameter. This result is interesting because it shows that both absorption and adsorption processes are capable of producing linear isotherms for low concentrations. At high solute levels, the solid phase concentration converges towards a constant value equal to A over B. This constant is often referred to as the sorbent capacity, and it defines a horizontal asymptote to which the isotherm rises with increasing concentration. The parameters are obtained by fitting collected isotherm data with the model. In the past, this has always been done by linearizing the equation and obtaining a least squares fit. However, nowadays, nonlinear regression programs are readily available and often provide better results. Having said this, I'm still going to briefly review how to linearize the Langmuir equation. To start, let's invert the equation and rearrange it into its slope-intercept form. The equation indicates that a plot of 1 over the equilibrium solid phase concentration of the solute versus 1 over the equilibrium concentration of the aqueous solution should produce a straight line. A fit of the line provides a slope and an intercept. From these, we can obtain the fitting parameters A and B. Let's go ahead and apply what we learned. The example provides the initial methylene blue concentration in an aqueous solution and the concentration remaining subsequent to the sorption process, in which 250 milliliters of solution was equilibrated with 2 oven-dried grams of cotton fiber. Part A asks us to determine the solid phase concentration and to plot the isotherm. The solid phase concentration is obtained from a mass balance. Although adsorption is a surface or interfacial process, often we don't have information on the specific surface area of the sorbent. In such cases, we try to use the same sorbent batch to ensure a constant specific surface area and report adsorption on a mass basis. Here, the plot of the solid phase concentration versus the concentration in the aqueous phase produces a curve similar to what we just described, the Langmuir isotherm. Part B of the example asks us to fit the isotherm data with the Langmuir model. For this, we will fit the linearized form of the equation, so we invert the isotherm data and plot it. Fortunately, it produces a straight line with a positive slope and intercept. From the slope, we obtain A, and with A and the intercept, we obtain B. There is a part C to this example, but before we work through it, let's review the theoretical development of the Langmuir equation. The Langmuir model considers the adsorption of a single solute from a solution at dilute concentrations onto a solid substrate. When the sorbent is submerged in the solution, both solute and solvent molecules can adsorb. Thus, what we're discussing here is more complicated than the partitioning process, in which the solutes move from the solution into a second phase. Here, the solute actually displaces a sorbate already adhered to the surface. To model this, we will make the following assumptions. First, the sorbent has a fixed concentration of surface sites, with each capable of holding just a single sorbent. Thus, adsorption is restricted to a monolayer. It is also assumed that the area and the energetics of each site is the same. That is, the surface is homogeneous. This also allows us to treat the adsorption process as though it's a chemical reaction in which a solute molecule replaces a solvent molecule at one of these sites, and this process is reversible. Finally, it is assumed that the adsorbed species only interacts with the surface and not with adjacent sorbates. This assumption, along with the restriction to dilute concentrations, allows us to replace all activity values, both solution and surface activities, with concentration. Now, to begin our discussion, superscripts are added to distinguish solute and solvent concentrations to make them more clear. The equilibrium constant for this reversible reaction can be defined in the usual way: the concentrations of the products divided by the concentrations of the reactants. Because the solute is at dilute levels, the concentration of the solvent is essentially constant. That is, desorption of water molecules from the surface of the sorbent has a negligible impact on the concentration of water in the aqueous solution. This allows us to combine the concentration of the water with the equilibrium constant, which we define here as K'. Placing the sorbent in the aqueous solution saturates the surface, with each site being occupied by either a solvent molecule, water, or a solute molecule. As a result, the total surface site concentration, which is a property of the solid, is equal to the sum of these surface concentrations. Substituting this in for the surface concentration of the solvent and the expression involving the equilibrium constant and rearranging, we arrive at the Langmuir equation. Given that the expression is in terms of only the solute concentrations, we drop the superscripts and return to our standard notation. Comparing this result with the empirical form of the equation used previously helps define the meaning of the fitting parameters A and B. Now let's finish the example we started previously. Part C of the example asks us to estimate the specific surface area, the area per unit mass, of the fiber, given that methylene blue occupies 130 square angstroms of area when adsorbed. This value is calculated using the concentration of surface sites, Avogadro's number, and the area occupied by the absorbed solute, methylene blue. With the Langmuir fitting parameters found earlier, the concentration of the surface sites is calculated, which then leads to the specific surface area of the cotton fiber. This appears to be an excellent approach for gauging the surface area of solids such as natural sorbents. Such values are quite difficult to gauge, especially in solution. A serious flaw with this approach is that it assumes that the molecule has a flat orientation on the surface. There is no evidence for this assumption. In fact, the assumed areas occupied by the methylene blue molecule found in other studies range from about 25 to 200 square angstroms. Thus, the measurement should be taken as a relative measure, which can be used to identify changes in sorbent area, for example, due to differences in processing. An advantage of the Langmuir model is its theoretical development, which provides meaningful parameters and deeper insights. For the parameter B involving the equilibrium constant, the standard free energy for adsorption can be obtained. Because water is the solvent and the solute is at dilute concentrations, this is in terms of the molar volume of water. The parameter can be used, for example, in examining how solute structure influences the adsorption energetics. Later on, we will review the Freundlich model. This model is thought to be applicable when the surface is heterogeneous. The heterogeneity is often modeled as a variation in the heat of adsorption. The heat of adsorption is designated with a capital Q and is defined as the negative of the enthalpy of adsorption. The remaining portions of B are then combined to form the pre-exponential constant. In textbooks and in the literature, this constant is often designated as B'. Thus, we've expanded our definitions for the fitting parameters as follows. What we're going to do next is return to our case study involving the sorption of aqueous organic solutes to processed wood fiber. However, rather than neutral species, we will consider quaternary amines, organic cations. As discussed in the previous lecture, wood fiber processed for the purpose of making paper carries a negative charge. This charge is a result of the ionization of weak and strong acid groups at fiber surfaces associated with the hemicellulose and lignin. As we will see, the specific adsorption of organic cations at these charged sites is a good application of the Langmuir model, with a few caveats. Later on in this course, we will look at various mechanisms involved in the charging of solid surfaces when they're placed in water. The ionization of acid groups is a primary contributor to the charge, especially for biomass. It can be thought of as a material's intrinsic charge because it does not require adsorption of charge-carrying components. There are various ways we can quantify surface charge. A common approach in this course will be with charge density, which is the charge per unit surface area, usually reported in coulombs per meter squared. The adsorption of organic cations involves the displacement of existing cations, usually inorganic, that act to neutralize acid groups. This type of reaction is suitably referred to as an ion exchange reaction, and the total concentration of sites, acid groups, available for the exchange reaction per unit mass is known as the solid material's ion exchange capacity, or IEC. In the case of acid groups, the phrase cation exchange capacity, or CEC, is often used. IEC is commonly reported in milliequivalents per 100 grams of oven-dried solid. Surface acid groups are usually monovalent and provide the same amount of equivalents as moles. That is why the values are reported here in either milliequivalents or millimoles per mass. Another value used to quantify the acid groups is the ion exchange density. This quantifies the charge on a per area basis. This is thought to be a more useful gauge of a surface's ability to participate in ion exchange reactions. Shown here are conversions between the different quantities discussed. Wood fiber processed for papermaking possesses a low ion exchange capacity relative to commercial ion exchange materials, but the values are significant enough that the fibers carry a relatively large ion load. Furthermore, molecular and polymeric additives used to aid in production or impart certain properties into commercial paper products are typically cationic, allowing them to exploit the ion exchange sites of fiber surfaces. Here, typical ion exchange capacities for pulped wood fiber, bleached to various degrees, are listed. It can be seen that with greater lignin removal, there is a lower fiber ion exchange capacity. In the previous lecture, it was mentioned that lignin removal is accompanied by the removal of hemicellulose, which possesses carboxylic acid groups. The reduction of IEC is tempered somewhat by the carboxylation of lignin that occurs during kraft pulping operations, and by its sulfonation in sulfite pulping. The IEC of processed wood fiber can be measured using conductometric titrations. The details of this measurement are provided in the supplemental materials. Next, we look at adapting the Langmuir model for ion exchange reactions at charged surfaces. The process again involves competitive adsorption between two chemical species. However, in this case, the sorbates are two ions. Usually considered will be one organic ion and one inorganic ion. In this case, the solvent molecules are not involved in the reaction. The adapted assumptions include the following. The exchange process is associated with specific ion exchange sites, and the energetics are the same for all of these sites. The sorbent possesses a fixed concentration of ion exchange or adsorption sites, which we quantify with the sorbent's IEC. Finally, we again assume that the adsorbed species do not interact with the surrounding sorbates. With these assumptions, we arrive at a form of the isotherm equation for the ion exchange reaction that appears to be problematic because it involves the solution phase concentrations for both of the competing ions. An approximate approach sometimes used for handling this argues that the following form is arrived at when the organic ion is at infinite dilution and the pseudo-equilibrium constant is defined as follows, and that this form of the equation holds for high organic ion concentrations relative to the concentration of the inorganic ion. Thus, this form of the equation is assumed throughout. The equation might be better described as being semi-empirical. In papermaking systems, Sodium levels are usually quite high due to the use of sodium salts in pulping and bleaching operations. Under these circumstances, the approximate form of the equation is likely accurate over the entire range of organic ion concentrations. Let us consider the adsorption of an organic ion to exchange sites at fiber surfaces, acid groups, which are assumed to be occupied initially by sodium ions. To avoid the need to take into account speciation, we will use a quaternary amine. It also ensures that both the organic and inorganic ions have the same charge number, +1, which will help emphasize the points we're trying to make here. The process will be analyzed using the approximate Langmuir model just introduced. While we are specifically looking at adsorption to plant fiber, the results apply to other ion exchange reactions, especially at or near the isotherms linear and plateau regions. By considering these regions, we will obtain valuable insights on water-based ion exchange reactions. There's not a trove of experimental data available on this system, but we can make some generalizations based on what is available and on the behavior of similar systems. For the dilute region, we expect linear isotherms with a slope related to the free energy for the exchange process. If we break the exchange process down, it involves the movement of an organic cation to the interface. This cation consists of a positively charged head group, which we can view as a point charge, and a linear alkyl chain, which we'll call a hydrophobe. We chose this structure rather than a quaternary amine to emphasize the role played by the hydrocarbon chain. The organic ion replaces a sodium ion at the interface. Using a somewhat superficial view, this can be thought of as the exchange of a +1 point charge in the movement of the hydrophobe into the interfacial region of the sorbent. Experimentally, such a transfer reportedly reduces the excess free energy of the hydrophobe by about 20%. As a result, the more hydrophobic the organic cations are, the stronger their tendency to participate in ion exchange reactions. This manifests itself as higher initial slopes for their isotherms. Now let's look at the plateau region for this organic ion. We expect the isotherm to climb asymptotically to the ion exchange capacity for the sorbent. However, for such structures, the isotherm will often climb above the IEC when the alkyl chain is beyond a threshold length. As the interfacial region saturates with the organic ion, it becomes more accommodating for nonpolar organic species. The larger the hydrophobe, the more significant this effect. There can also be a reversal of the surface charge for linear alkyl chains greater than about 8 carbons long. In general, the factors influencing the tendency of organic ions to participate in ion exchange reactions at surfaces have little to do with the nature of the charge. Due to the strength of coulombic interactions, charge number remains the primary factor. For example, a +2 ion adsorbs more strongly than a +1 ion at a negative surface. Nevertheless, the nature of the surrounding chemical structure also plays a role. For the same charge number, ions possessing less stability in water will adsorb more strongly, and those possessing large hydrophobic groups can increase sorbent capacities for retaining organic ions. Seems like this would be a good time to review some examples. The first is a straightforward calculation, but it makes an important point. Here, we add processed wood fiber to an aqueous solution containing more than enough tetraethylammonium chloride, or TEAC, to saturate fiber surfaces. The example asks us to estimate TEAC's molar concentration in the aqueous solution after we separate it from the fiber. What is interesting here is that 4 ethyl alkyl groups surround the charged group. However, this structure does not increase the sorbent capacity, likely because it is not a single long flexible chain. In other words, the structure of the ion's uncharged components play a role in determining its absorption behavior. Next, consider the adsorption of ethylamine from a solution containing sodium chloride. The solid, which could be a modified fiber, sediment, or clay, has a cation exchange capacity, a CEC, of 1 milliequivalent per gram. Here, speciation must be considered, but with a pH of 7 and ethylamine having a pKa value greater than 10, the solute is assumed to be ionized, that is, in its conjugate acid form. Part A of the example asks us to plot and fit the provided isotherm data to obtain the Langmuir fitting constants A and B. It also asks us to mark the cation exchange capacity line on the figure. With the constant B in the sodium chloride concentration, we can estimate the free energy for the ion exchange reaction, which is part B of the example. Interestingly, the free energy associated with the transfer of a methylene linkage out of water is about 4 kilojoules per mole. If we assume it's about the same for a methyl group and take 20% of the free energy associated with the transfer of 2 methylene linkages out of an aqueous solution, it should be close to our free energy value. Well, it is, emphasizing the more favorable environment near the interface of the solid. Next, we take up the Freundlich model, which after the Langmuir equation is the most commonly used model for fitting adsorption data. Shown here is the general shape of the isotherm curve. The derivative of the isotherm is positive and decreases with increasing solute concentration. There is no linear portion at dilute concentrations or a horizontal asymptote. The curve climbs with a continuously decreasing slope. Unlike the Langmuir model, which has a theoretical foundation, the Freundlich equation shown here is purely empirical. The constant 1/n is known as the intensity factor. For the absorption of aqueous organic solutes to a solid phase, this value ranges from between 0 and 1, with increasing values associated with stronger absorption. The Freundlich constant, Kf, is often found to be proportional to the sorbent capacity. The Freundlich equation is best fit using nonlinear regression, but it can also be linearized in fit. Here it is shown how to linearize the Freundlich equation. This process involves taking the logarithm of both sides and rearranging the equation into its slope-intercept form, which indicates that a plot of the logs of the solute concentration in the solid phase versus that in the aqueous phase should produce a straight line, where the slope is equal to 1/n and the intercept is a logarithm of the Freundlich constant. For absorption from an aqueous solution, the slope is usually positive and the intercept is negative. This example provides data for the adsorption of trichloroethylene or TCE from an aqueous solution to zeolite ZSM5, a sorbent reportedly better than even activated carbon for stripping such chemicals from water. The first step is to take the logarithm of the solid and aqueous phase concentrations and plot them against each other. The slope and intercept of the line provide the values we're after. The units always seem a bit odd for the Freundlich constant. While the Freundlich equation is purely empirical, there have been efforts to derive it based on a set of physical assumptions. An approach that provides some useful insights assumes the Langmuir model but varies the heat of adsorption. In other words, it assumes a heterogeneous surface. The functional form for the fractional coverage of the surface is given by the integral of the isotherm model multiplied by the normalized distribution for the heat of adsorption. The model assumes that the Langmuir equation gives the fractional coverage for a given heat of adsorption. Rearranging provides a form that can be integrated, but arriving at the final form of the equation is a little bit complicated. There is no guarantee that this derivation is unique, thus the successful fit of isotherm data using the Freundlich model is not considered confirmation that the surface is heterogeneous. However, in practice, better fits of isotherm data with Langmuir versus the Freundlich models tends to be treated as evidence for lower and higher degrees of surface heterogeneity. Before we finish up, let's briefly review the major concepts presented. The focus has been the absorption of organic solutes from an aqueous solution. The stability of a solute in water helps determine the extent of the absorption, regardless of the mechanism involved. We have already discussed the impact of temperature, pressure, ionic strength, and ionization on the excess free energy of a solute in water. For adsorption, which we will use interchangeably with the term partitioning, solutes move into the bulk of the solid phase. It is assumed that this is analogous to the partitioning between water and an organic phase, where the free energy of transfer is the difference in the solute's excess free energies in the phases, a value often dominated by the free energy associated with the solute's movement out of the water. This observation helps explain the success of linear free energy relationships. In adsorption, uptake of solute is restricted to the surface, and competition and saturation influence isotherm shape. As with partitioning, adsorption from water can be driven by solute stability in the aqueous phase. That is, the solute is being pushed out. It can also result from attractive interactions between the solute and surface, as in the case of ion exchange. In other words, the solute is pulled to the surface. Often both a push and a pull are involved. As we shall see, sorption plays a vital role in colloidal science. Surfaces of particles placed in water quickly change as charged and uncharged species adhere, which governs the generation and demise of these colloidal systems. This completes our introduction to the sorption of organic solutes from aqueous solutions. If you have any questions, comments, or corrections, please contact me directly.